Hello, welcome to more Haskell live streaming. This week I want to pick up where I left off last week, where I started to implement the basics of calling functions in my VM. So I added a couple of new instructions, call and return, and I tried to implement them in the VM, and that all went fine apart from the fact that it didn't work. So I want to fix it today, but I don't want to just directly fix it. I actually want to add a new instruction called trace. And the thinking for trace is that it'll dump out some debug information of the VM as it's running. But to do that, I think I want to refactor a little bit about how the VM's implemented. Basically make step only do a single step and then wrap the iteration somewhere else. What else? I want to add trace. I want to do that refactoring. I want to undo some work I did last week. So I changed the stack from being just a normal list in Haskell to being a sequence because that made it easier to jump back and forth. I thought of a better way of doing. Well, I thought of a way of doing that, keeping the list, and the list is actually a better data structure for pushing and popping onto and treating it like a stack. So I think I'm going to undo that. I think that's the plan. So where I left off last week was this piece of code, this test that was failing. Incidentally, I think I know why it's failing, but rather than just jump into fixing it, I think I'll do the refactoring and the tracing to prove the hypothesis, and then I can come back and look at the code and see if it works. I'm just going to turn on line wrapping. No, let's toggle something. Word wrap. Okay. What I think the bug is incidentally is this. So I said call 7, that's the wrong address. It's wrong for two reasons. One is it should be call 9. When I worked out last time, it should be jumping over these two instructions and starting here. It's not doing that. But also I'm not zero indexing, I'm actually indexing from 1. So this is the return address. It should be 7, except it shouldn't be 7, it should be 6 because it starts from 0, not from 1. And this is the call address. It should be 8 and not 7, basically. I think that's what it is. But I'm not gonna test the hypothesis yet. I'm actually gonna go and see if I can improve the VM and add this new instruction called trace. And I might make this really big actually. I might just stick at the end, so I might do 0xff or something like that, and I just put it right to the end. And I will make this an instruction. Okay, so some refactoring. Let me get rid of the sequence stuff first. I'm going to go back to just using a stack. Not a stack, a list. Sorry, it's my stack. Let me just, can I comment that out? Not like that, I can't. I don't know how to comment that out. That one, there we go, comment that out. Let me just do it for a second. I'll come back and do it later. But let me go back to doing CPU stack is just a list int. Okay, and then I can get rid of that because I'm not going to use sequence anymore. And then we'll just fix all the errors. Just fix them all. My plan for this, I'm going to do a fancy drawing thing again. So the plan for this is the reason I use a sequence actually is I want to treat the memory a little bit like this, or the stack a little bit like this. And we start to put stuff on. And let's say at this point we do a call, which means that we want to then return to here. Well, it's actually off by 1, but it's that kind of thing, which means that I need to take the address of this. So that when we get to our return instruction, we can say, okay, we know what the address is here. We want to kind of jump back to this point. So when we're doing the return, we want to be able to say go back to this. We need to know the address of that position in the sequence. If you have a list, it's expensive to kind of jump around to specific places or to even know. I mean, the list works the way around actually. So, oops. If we have a, can I scroll? No, I cannot. If we have a list, you're always pushing stuff onto the front. Can I stop now? No, it's not. So if this is your list, at the point at which you say call, you're always at position 0 anyway. And then you add some more stuff on, and it ends up being added to the front, and then you don't know where to jump back to. You can't jump back to 0. But my thinking for this is, I'm actually just going to keep track of how big the list is. So I could do it by calling length, but length is a little bit expensive to do every time I want to use the list. But what I could do, I need a bigger eraser. What I could do is store two things. One is the list itself, and the other is a count. So you could say initially like count equals 0, and we have an empty list, and then we push something onto the list. So our stack becomes this, and then obviously count would then become 1, and so on. So at the point at which we get to call, we should know how long our list is. Right, so imagine this is the point at which we get call. We can now say, okay, count is 4. And then when we do our processing for the actual code in the function, you're going to push and pop stuff. So every time we pop, we decrement the count, whatever. But we'd say, okay, it was 4 when when we get to call, what I'm going to do is take the current count and just put it into the stack at the front, because that's how we put it on the stack. Okay, then we do our processing for function. So let's say we do a couple of things. So now our length, we know, is going to be 7. So it's the number 4 we pushed on, and then two extra things for the function. Then when we hit return, what I want to do is say, oh, it doesn't work, does it? Because I don't know. No, that's all nonsense. I was going to say, I could then work out the difference between the 7 and the 4 and see that I need to pop 3 things. But to get the 4, I need to know where that is, and I don't. Okay, so this whole thing isn't going to work, so I will leave the sequence in place. Damn, that's annoying. I still need to know where to jump back to, which means I need to know, oh no, we have a stack pointer. So maybe the stack pointer I would set to be 4. The trouble is, if you call another function, you lose that. No, the stack pointer just needs to point to where you are, where that stack frame is. Hang on, let me go back to here. So this would be the stack pointer. It's going to point to the start of the stack that's being used right now. So to pop that, we take count minus stack pointer, and then we just pop those things off. That's all I need to do. I don't even need to store 4 in there. That wouldn't happen at all. This would just be 6. Yeah, so when we say call, we'll take the current count, put it on, set stack pointer to be that. When we call return, we'll work out the current count minus the stack pointer, and we will pop that many elements off, and that should give us back the stack that we had when we called. Okay. So I can go and do this, I think. I'm going to spend all evening going back and forth on this probably. Okay, so this is not going to be sequence event, it's going to be this. And then we got lots of problematic things here. So let's just fix the errors one by one. So that's going to be an empty list. Right, this is destructuring. So I think we can do this. And then this. And this, maybe. So this is going to say if we have, okay, this is what we call halt, is if we have anything in the stack, we just sort these around. So if the stack is empty, we'll complain about it. Otherwise, if there's a single thing in there, we don't care if there's anything after it, I guess. We're going to take the front of the stack. Yeah. Take the front of the stack. Where's that character gone? What am I doing? I've completely forgotten where underscore is. That was very strange. That's minus underscore. Wow. Mine went strangely blank there. Okay. When we're calling halt, if there's nothing in the stack, we complain about it. Otherwise, we take the thing off the top of the stack and we show it. We're basically popping at this point. This thing, we are going to use this count. So we got stack and we got CPU stack length, which is going to be an int. I'll write it out. Okay, so here we've got a stack pointer is 0 and CPU stack length is also 0. Okay, so here, touch stuff onto the new stack. Oh, this is for call. We can come back to call in a second. The stack pointer I think we set to be the CPU stack length. CPU stack length. So we'll need to destructure that. CPU stack length. It's something very long. Okay, this is going to be broken. So new stack, I think, is probably fine. I don't think I need new stack because I don't think we need to push onto it. So all I was pushing onto it was the CPU ID plus IP plus 2. So I was pointing two instructions further forward. So I think I was trying to push the return address onto there. Which I will still do. Okay, so we've got two things to worry about. One is where does the stack pointer go back to, and the other one is where do we set, what do we set the instruction pointer to, and that's what we will put into the stack. So this we're going to take CPU ID plus 2, and we're just going to put that in the front of the stack. Okay. Return is complicated. Let me come back to call and return in a second. Let me just fix these errors first. So I think we just do that, but we need to swap the order around a little bit here. So the stack at the head of the stack is X and then Y and then Z's, and then we're multiplying. Then what we're going to do is take X and Y and multiply them together, take the result of that and push it onto the list at the head of the new list. Here for addition, it's going to be the same thing. Oh, this is subtraction, sorry. So we take, we're going to swap these around, I think. Actually, Y minus X. So we do our subtraction, we push it onto the stack up here. X, Y, and Z's, then we take X plus Y, and we push it onto the stack. Okay, so now we just do this stuff. So return value is not quite what we want to do. So when we call return, what do we want to do? So the new stack, what we do is we take the old stack, CPU stack, and oops, we just drop the difference between the current pointer, sorry, the current length, and this stored pointer. So we can say something like frame size of CPU stack, and we'll say frame size. Frame size is going to be CPU stack length minus CPU stack pointer. Okay, that will get us back to the, what will that get us back to? That was going to get us back to the original stack, the stack as it was before I called the function. Just describe this as CPU stack length. Okay, now the return address we are going to put into the stack at the original stack. We're going to put it into there at the address of CPU stack pointer, I guess. Maybe. So what are we going to do? Oh, this is probably going to be wrong, but we can take CPU stack and we can just pop it, I think. We said non-empty, not ordinary lists. Oh, this could be empty. Right, what else can we do? So I just want an unsafe thing here because I think I know what it's going to look like. I want to, if I jump back to, hang on, let me think about this. Let me just clear that and start over. So an actual example, I'm going to start from the right and work left. So let's imagine our stack has got, I can't remember what was in my program, it's something like, it doesn't really matter. We can do, let's say we push 2 and then 1 onto the stack. Then we want to call, so at that point, the return address, let's say the return address for some reason is 4. This might not be the case, but let's imagine a program for some reason the return address is here. Okay, what we should probably do, I think, is then set the stack pointer to 4 rather than to 3. That makes sense. Okay, and then we do some stuff in our function. So let's say we push 4 and 9 arbitrarily, and 11, I don't really care. And then we come to the return. So return value I can worry about later. No, I'm not going to worry about later. I'm going to worry about now. So the head is going to be our return value. So what I can then do is, well, at this point as well, so the length is going to be 6. So this is not 4, this is actually 3 because we're 0 indexed. Okay, so what I can then do is I can say, instruction I can do, I can say drop 3. And what that should do is just chuck away these ones. And now our length will be 3. So at this point, len equals 3, and our stack is the stuff that's not crossed out. Okay, then I can take the head of that list somehow, and that's going to be, it's going to give me the value 4. Oh, before I drop 3, or it doesn't matter because everything's mutable, but I want to capture this value 11. So I'm going to take the head of the list, and then we should be left with 1 and 2. So I'm basically going to split it here. And I'm going to push the value 11. So now my stack should be 11, 1, 2. And my next instruction, so this then becomes the IP, is going to be 4. That's what I want to do when I call return. Okay, let's give that a go. So return value is just going to be the head of CPU stack. So I need to work out some kind of unsafe head. Is there any kind of, yeah, there we go. Oh, that's not what I want at all. Well, there's nothing in the stack. from maybe 0. Oh no, it's not from maybe. Sorry, it's just maybe 0. Something like safe head. No. Oh, I've forgotten really to go from. It's head-like, but it has some safe form. Maybe head. Oh, give me something. Will it suggest anything? Oh, that. What does that do? Head 1 foldable FA to A. But it needs to be foldable 1. I don't know what that is. Module prelude, and then we want to go from list of A to A, prelude to unsafe. Okay, and what's a safe equivalent? List to maybe turns nothing, or just A, where A is the first one on the list. List to maybe. Okay. List to maybe. CPU stack. What's this problem here? So goes list of A to maybe A. Can match type A to B. Match type maybe int. Is it this that's wrong? So maybe goes. Ah, this is not the right function. I think it is from maybe. Okay, so we'll get it back. If we don't get returned back, we just pretend it's 0. That will somehow be fine. Okay. New stack is not going to be this now. This is actually going to be out of frame or something like that. I think we call it out of frame. So that's going to be this stack as it was before we started doing the function stuff. Okay. The return address now is going to be from maybe. I'll do the same thing. It's not a great solution, but that should kind of work. And then we can say new stack is tail of outer frame. Tail is not safe either. Unsafe tail. No. Just want the unsafe version. Can I import that? Will it help me import that? Import prelude hiding head and tail. Import prelude unsafe, I think. Need the extra. Not unsafe. It's just really unsafe. Okay, and we'll pull in head and tail. Okay, so where were we before? Somewhere in here. Oh, I want to hide from prelude, not from prelude. No, everything's very unhappy. Okay, it gives me head and tail. So new stack returning properly, but actually we want to take return value and we want to put it onto the head of that list. All right, we want to push it onto our stack. Okay, some more errors, hopefully. So here we're going to say, what's this doing? It's getting too long now. It's when we push stuff onto the stack, it's going to be from integral v, and we're going to push it onto the CPU stack. Okay, getting there slowly. A lot of refactoring. Step halt. Doesn't take a sequence of ints, it takes a list of ints. Okay. Does any of this work now, I wonder? I'm hoping for one failure in tests. I'm hoping for compiling first, actually. That's going pretty well. One failure in the test. Okay. We haven't called functions. This is the thing that's wrong. Okay, next thing. I want to look at this idea of step. So what we got here? Okay, step all of this so we can say, just split some of this out a bit to make it more readable. Can I say that? I cannot. Can I say that? Yes-ish. If I just take this and I can just say initial CPU is of type CPU CPU, and then initial CPU is that. Right, that doesn't work. I need the constructor here. And then here I can say initial CPU. It's a bit shorter, okay. Okay. When we call hold, we're not saying anything about having terminated, we just don't recurse here. So I want to add something to my CPU. And I can say CPU halted is a bool. And then down here I can initialize it. Hopefully it'll reformat it for me. I can say CPU halted is false. Okay. And then I can say something like while not CPU halted. Is while a function I have access to. Let's do this bit by bit. Well, REPL. What's the type of while? Not in scope while. There's something I can do which is while like. I can't remember what it is. Is it like an until loop while? Oh, it was an until. Okay, until takes a boolean, a function, and an initial value. Okay, so it'll be until the function we're going to call is CPU halted. I'm going to say step, which goes CPU to CPU, hopefully. It's not going to give me any errors back though, but if it did go CPU to CPU, we'd be okay. It's going to step on a program, and it's going to take an initial CPU. Okay, I'm going to call this go. So we return a string. I'm trying to think how that would work. I know I want the type of go to be CPU to CPU. Oh, it's got a program first. Program CPU to CPU. And the errors come in when I don't recognize instruction. So maybe I could just store it in here for now. CPU error is empty. CPU error is a type of text. Oh, we've got one called CPU error already. Maybe a string. Okay, we'll just use that. So Go program I can just call step program. I fix that in a second. And then we can say bring this back in. So here I can say the thing we're going to return is case file CPU no. When we run the program, we're going to get a CPU back, and what I want to do is set the error if we get an error. So if we encounter an error anywhere, we should have put it into CPU error. So if it's set, we return that. And if it's not set, then we return V. And what's V? V is the head of the stack. Okay, so it's going to be the result. The result of the final CPU. Where? Let's do it this way. What a mess I'm doing behind. Okay, so final CPU is going to be that. So the final CPU, we just run it until we've halted. And result of CPU where CPU error is just error. Good point. We can't pass in that. We pass in P. I will not scope until anyway, sorry. The result of CPU with an error is that the result of CPU where CPU stack is empty is whatever the error message was, unexpected empty stack, unexpected empty stack, and the result otherwise, well, we need to destructure this. So CPU stack where this is equal to x and whatever is just going to be show x. Okay, so we need to fix this up so this type will match. Can we put in until? GHC base until, prelude until. Nope. is really get rid of it. I'd say module prelude. No, not having any of it. Okay, because it's something like 4M and the modal we can use is identity. Is that a thing? Haskell for M underscore with identity. This is a horrible way of doing until. No, let's not go there. I take it the implementation is quite easy. Yeah. Why is that not re-exported? Can I put that one? That looks better. Okay. So now it's going to about step P. Right. So this needs to go CPU to CPU. Okay. If it's already got an error, we don't step. Just put down CPU. Okay. If there is no error, then we get our instruction. If it's halt, we call this. So halt, I'm going to change to return this signature, I think, and it's going to return just the original CPU, but we will set CPU halted to be true. Okay. Next one. We're not going to do the stepping. So step. When we call push, why does it need the program? Because we're trying a new CPU. Okay. That looks okay, we just didn't recurse on that one. I'll come and tidy these up in a moment. Okay, and then this one might be okay. Sorry, that's complaining because of this reason. We're not destructuring the stack at all, it's using the pointer. That'll change in a moment, but we can change it later. Okay, otherwise, what have we got? We're going to return the CPU we had, but we're going to say CPU error is just that. Okay. In theory, that might work. Let's see. So it's just one failure, which is the function calling. Looks good. Okay, a lot of work. The reason for that is I thought I could say run trace, which goes program to IO string. So run trace is of some program P, so we can then call run P. But for each step in this, we want to pretty print the CPU. So something like this is where I'm going to use 4M, I think. And then what does 4M look like? Is mapping with its arguments flipped. Okay, but what are its arguments? So it takes something foldable. Is this foldable? It is not foldable. I can make it foldable, I guess, but that might be quite difficult. This needs something foldable. Replicate M. No, it just does it that many times. When? So when bool do something. Maybe I could use when. I'm not sure. But what I want to do basically is run P, and for every step in P, for every step in P doesn't make sense. It's actually, I want to call step and then print and then step and then print. So it says until I want to kind of hook into. So let me do the copy and paste approach and then come back and see if we can work out a better way of doing this later. So do we have some equivalent of until, but yeah, I go away for a second. Okay, it doesn't do anything different at the moment. So what I would like to do, I think, is recurse here. Instead of saying until, I'm going to write my own sort of recursive thing. I think thing there meant function. So go is of type CPU to IO CPU. So we're going to call go with the initial CPU. And then go with the CPU where it's halted. CPU holding goes true. When it's halted, we just stop. Okay, and then go with any other CPU is this is where we're going to trace it, I guess. So what are we going to do? We have the CPU, we want to print it. Pretty print our CPU. And then say let CPU equals step P CPU. Gives a different name, just to make it clear. And then we will return go CPU prime. Okay. However, in this case, we don't return pure CPU, we return pure result of the CPU. And then we can say pretty print goes from CPU to IO string. Pretty print. I guess we can destructure this a little bit, so we could say stack. No, CPU stack. CPU IP. Yeah, for now, and we could say extra. We just say print, I guess. CPU stack. We're not going to turn a string here, sorry, it's IO void. So we're going to print that, and then we're going to put strlen, and then we're going to, I guess, print the CPU IP. And then put strlen that. Okay, so what's going wrong here? So couldn't match type CPU with list of characters, so this is not IO CPU, this is IO string. Okay. So now I think I can export that. And if I just come grab my spec, let me take a working one. So let me just grab this, reload, import VM, have it smaller, so I can say P is that thing. Nope. Not what I expected. Oh, it's a VM.program. Nope, I'm not exporting that. Can I say it is list of word 8? Yes. Okay, and then can I say vm.run p? This should be a vector word 8. Import data dot vector dot unboxed. Wow. Data dot vector unboxed dot from list there. P. Okay, try it again, but we'll call it P prime this time. What's type P prime is a vector word 8. Okay, so now I can call vm.run P prime. Yep. And can we say run trace? Yeah, it's not great, but okay, empty stack, position 0. Stack with 2, position 2. So maybe I want to be grabbing the thing out of the VM, but it doesn't matter, I can see it here. So empty stack, position 0. Position, so we've pushed 2 onto there. We're now position 2. Then we push 3 on, so we've got 3 and 2 on the stack, makes sense. We're position 4. And then we are multiplying. Okay, it's pops and it pushes. And there we go, that's kind of cool. Right, so if we go back to the VM and just look at these, where were we? Pretty printing. I don't need extra things. Yeah, do want the CPU ID though, because it's important for checking the function calling. Okay, so back to here. So now we can say from list, but now we're going to say this stuff. And it's a type vector of word 8. Okay, and then we can say vm.run p prime, get the wrong answer out. Oh, what have I done? I've pasted the wrong thing, haven't I? Yep, that's giving me the wrong thing. this is a copy and paste. That looks better. Is it going to complain now that p prime is already assigned? Yes. Is p assigned? No. So type of p is now vector word 8. So we can say vm.run p, and we get this weird answer out. And then say run trace. So position 0, empty stack. We run push, so we get position 2 in the stack. Then we get another push, so we get position 4, 3 and 2 in the stack. Then we call multiply, so we get 6. Makes sense. And we move forward 1, so we then call with the value 7. So this is position 5, it's position 6, and it's position 7. Okay, that's a good place to come back to. So this first 7, I think is here. However, we set the IP to 7, which is here. And it should be 9. So now that we have our tracing, can we test this theory? I don't think this will work either because I've not done the length thing properly. But anyway, let me just see what happens if it sets to 9. Okay, that's what happened because it's jumping back and then it's jumping back and forth. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That should be the correct place to go to. However, it's not popping properly. So return is broken, but it's not a big surprise because I kind of only half wrote the stack length thing. So I think what I want to do is create a couple of functions, helper functions. Well, I put them, let's put them at the top. So we can say, those all belong together. Let's go after that. So we can say stack push goes from, what do we push onto stack? An end. No. CPU, an end, and a CPU. Okay, so we can say CPU at, we'll destructure some parts of it, so we're going to grab the CPU stack and the CPU stack length. And this is going to be CPU, but we're going to set the stack to be this new value. Sorry, I missed the value out. It's going to be X pushed onto CPU stack and CPU stack length. It's getting too long now. This is increment CPU stack length. It's not increment, it's successor. Okay, so that's what happens when we push something onto the stack, and then we say stack pop goes from CPU to CPU, tuple, CPU and int. Because we'll return the thing. I might swap these arguments around, so we're going to go int and CPU. So stack pop. Just copy that for a second. So stack. So again, stack pop here. Okay. So we will say, let's use the unsafe head thing again. So we're going to return some value and the new CPU. Where B is head of CPU stack. Is that right? And CPU prime is equal to that, I think. So it's not going to be a successor, it's going to be the predecessor. Everything's bad here. Why is that unhappy? Oh, because I have an extra argument, that's fine. Okay, and this is going to be the tail of CPU stack. So unsafe, but easy to write. And I just need to find anywhere I touch the stack. So this is going to be, I've got these right around, haven't I? Push CPU stack. No, it's not push, so it's something like push stack. What do they call it? Stack push. Okay. Not great. Oh, we take a CPU and a value, not a stack. And it returns a CPU. Ah, we have a problem now, okay. So the other thing I want to do is get rid of this. But let me just update the record twice. Okay. This is horrible. So we push our thing onto the stack, and then we double increment the IP, the instruction pointer. Nasty, nasty stuff. Here, new stack. Again, we don't want new stack. Oh, maybe I should just return a stack. No, the whole point is I want to update the CPU. CPU prime of that, where CPU prime is stack push CPU and then CPU IP plus 2. Okay, I guess generally speaking we shouldn't be destructuring the stack in most cases. Oh, this is really annoying. Because I need to pop 2 things off it. And then I need to push something onto it, and each one is modifying the CPU in place. So it would be something horrible like let x CPU equal what is it, stack pop CPU in let y CPU equal stack pop CPU in then we can say stack push CPU and x plus y. That's if you have enough stuff in your stack. Let's assume it's fine. So then we want to say let CPU equal that in see that. Really nasty. This is not nice at all. I might need to make that better. And they're all going to be the same, aren't they? So then we can say step op takes the operator CPU and returns new CPU. Let me say step op of that is that. Okay, so we know it's int to int. No. No. Could might expect to type int to int, but actually type int. Why can you not do that? Oh, because it's int to int to int, that's why. It's two values. Okay, so then step add, we can say step op plus op minus op multiply, and then we'll ditch these things. Okay, does that work at all? Like, I think colon returns will be broken, but that's not a good sign. It's running forever. Stop. Okay, time's getting on, so I'll come back to this again next week, I think. I haven't added my trace function. I've just done this run trace, but anyway. Yeah, I guess this is the one that's broken. Let me just delete that for a second. Run the tests, see if the other tests work. One failure. Oh yes, okay. A failure makes sense. Some step up. I need to flip these around. Okay, so the tests pass, but functions are not safe to call because something's going horribly wrong. 0, 1, 2, 3, 4, 5, 6, 7, that should be the return address. 8, 9 should be the place we jump to. And then it should be pushing these on and calling return. Return is probably not working. That's the one that's probably broken. I wonder if I can quickly fix this. Okay. So what are we doing? We are let me just hold after the first one. And then I can come to here and I can reload. Just have a look at this. Oh, it's not in scope. Okay, so let's call it P again. So this is what I think is the correct code. Run debug. No, run trace. P. Okay, so what have we got? I'll just do one run through this, see if I can work out what's happening. So empty stack, push 0, position 0, position 2, and we've pushed 2 onto the onto stack. Position 4, we push 3 into the stack. Then we multiply. So now we're at vm.call, and multiply is pushed 6 onto the stack. That's good, I think. And call will push 7 onto the stack. So this is 5, 0, 1, 2, 3, 4, 5, 6, 7. So it should return to there. And we've jumped to 9. So 7, 8, 9. Okay, then we push 1 onto the stack. That's good, and we jump forward 2. We push 2 onto the stack, we jump forward 2. Then I expect next thing to replace 2 and 1 with 3. That's good. And we're at 14. Oh, and then we halted. Okay. It's the next instruction I want to see. When we call return. So where's this thing? So when it's halted, we want to do print CPU boring form. Okay, and when we're pre-printing, we can say, not that one, I can say print, but here we can say string. Oh, actually, no, it's fine. Let's print. I was also going to print out the length in case it gets it wrong. Oh, it's a stack pointer, that's what I wanted. Extra line. Show that. And then show CPU SP. Print that, and print that, and print that. So stack pointer, CPU ID. And it's what we call in call. Call stack pointer is new stack pointer, which is the current length. Okay. And we get the answer 3 coming back. Okay. So this is where we do a call. And we're going to say we want to drop 2 things off the list. Well, we're saying that it was of size 1 when we called. So what seems to have happened is we've dropped the last 2 elements off. So we say drop 2 from 1, 2, and 3. something here. I don't know what's happening here. What's the type of A? What's the type of drop? Why is it not showing me something nice here? Okay. Oops. Drop to from 1 to 3 gives me 3. That's kind of what I expected. When I saw the output from before, it left the thing at the head and dropped the tail. No, that does make perfect sense. Does it? I'm just out by 1. I think it's the only thing here. So 6 was on here. In 176 and 376. What we should have done is grab the 3, jump back to here, read this as our next instruction. So there's something wrong in return. Okay, at least I can see that return is wrong. I'm not surprised. It's a bit of a mess. Right, I'm going to stop now. I'm half an hour over time. Next week, I will come back and fix this properly then, so that return works. But yeah, thanks for watching along, if you lasted this long. And next week, I promise I will get call and return working. And then we can start to look at, well, I guess adding it to our input language and generating this, but also we need to look at parameters to be passed in as well, which means looking at variables. Cool, but that's all for next week. So I'm going to stop for tonight, and yeah, thanks for watching. Hopefully see you next week. Goodbye.